On the morning of January 16, 1943, a profound and unsettling silence was broken in the harbor of Portland, Oregon. The SS Schenectady, a Liberty ship barely 10 weeks out of the Kaiser shipyards, rested at her dock, a symbol of American industrial prowess. The conditions were idyllic. No enemy aircraft threatened the skies, no U-boat lurked in the depths, and the water was a placid mirror. Without any external provocation, a sound like a massive rifle shot echoed across the wharves. In a sequence of events that defied contemporary understanding, the vessel underwent a catastrophic structural failure, her hull fracturing completely from her main deck down to her keel. It was as if an immense, unseen blade had cleaved the ship in two. Sailors, going about their routine duties, were thrown into chaos as the bow and stern sections of the ship began to sag away from each other. The vessel's spine shattered while she was securely moored in the safety of her home port. This was not an isolated incident. It was a symptom of a terrifying and widespread epidemic. That same winter, the SS John P. Gaines suffered a similar fate, breaking apart in calm seas. The SS Manhattan, a T-2 tanker constructed with analogous methods, developed such severe cracks that her crew, seized by panic, abandoned ship. The period spanning 1943 to 1944 witnessed an alarming statistic. Over 2,500 Liberty ships reported significant structural failures. These were not minor issues. They were profound breaches, gaping cracks in hulls, fractures across decks, and catastrophic splits that compromised the very integrity of the vessels. At least 19 of these ships broke entirely in half. 3 more simply vanished somewhere at sea, disintegrating with such rapidity that they could not even broadcast a distress signal, their disappearances remaining permanent, tragic mysteries. These were not casualties inflicted by a wartime enemy. They were ships that were, in effect, self-destructing. The context of this crisis made it all the more dire. The United States had staked its entire wartime logistical strategy on the success of the Liberty ship program. In the aftermath of the attack on Pearl Harbor, which thrust the nation into a global conflict, there was a desperate, urgent need for cargo vessels, hundreds of them, and they were needed immediately. Conventional shipbuilding techniques required an average of 8 months to produce a single vessel. This timeline was untenable. Into this breach stepped Henry Kaiser, an industrialist with no prior shipbuilding experience, who made an audacious promise. He proposed to mass-produce freighters using principles borrowed from the automotive industry, assembling them like automobiles on a production line, reducing construction time from many months to a matter of mere weeks. His shipyards in Richmond, California, became the crucible for this industrial revolution. They employed radical new techniques. Electric arc welding replaced the slow, labor-intensive process of riveting, and prefabricated sections were constructed in dedicated shops before being assembled into a complete hull, much like a colossal three-dimensional puzzle. The logistics were orchestrated with assembly line precision. The results appeared miraculous. By late 1942, Kaiser's yards were launching Liberty ships in an astonishing average of 42 days. The national propaganda machine celebrated this achievement. Newsreels featured the iconic Rosie the Riveter figures, though they were now often welders, showcasing their role in transforming steel plates into ocean-going vessels at an impossible pace. The SS Robert E. Peary set a seemingly unbelievable record in November 1942, being constructed from keel laying to launch in just 4 days and 15 hours. The nation cheered. The relentless attrition of Allied shipping tonnage by German U-boat wolf packs was finally being countered by a flood of new, American-built hulls. Then, the ships began to break. The failures were not the result of torpedo strikes or the fury of North Atlantic storms. They occurred spontaneously and catastrophically in conditions that should have been entirely routine, in calm harbors and on gentle seas. Naval architects and marine engineers were baffled. Initial inspections revealed that the welds appeared sound and met quality standards. The steel composition conformed to specifications, and the designs were based on proven British blueprints. Yet the Liberty ships were fracturing with the unsettling fragility of fine porcelain. The cracks typically originated at points of sharp geometric transition. The corners of hatch openings, the bases of gun mounts, the squared-off edges of the hull itself. Once a crack initiated, it would propagate through the continuously welded steel plates at a terrifying velocity, sometimes racing the entire length of a ship's hull in a matter of seconds, unzipping the vessel before any corrective action could be taken. The United States Maritime Commission convened emergency investigative committees. Metallurgists subjected samples of failed steel to intense microscopic scrutiny. Engineers painstakingly re-evaluated every stress calculation. Naval inspectors swarmed over damaged vessels with every measuring instrument available. The search for a singular culprit was frantic and exhaustive. Was it substandard steel? Faulty welding technique? Inherent design flaws? Inadequate quality control? While the committees debated, the ships continued to fracture. A palpable sense of terror grew among the merchant marine crews who sailed these vessels. They lived with the constant, gnawing fear that the hull beneath their feet could suddenly and without warning split open, plunging them into the lethally cold waters of the Atlantic. The industrial miracle of mass production had transformed into a maritime nightmare, and no authority could provide a definitive explanation for why these ships, built in record time, were failing in record numbers. The breakthrough, paradoxically, did not emerge from the hallowed halls of academia or the sterile environment of a research laboratory. It came from the shop floor, from an individual who was not supposed to question the decisions of the engineering department. Bessie Hamill worked the graveyard shift as a welder at Kaiser's Richmond Yard No. 3. She was one of the thousands of women who had entered the industrial workforce, filling the vacancies left by men who had gone overseas to fight. After 8 months of welding massive hull sections, she began to notice a pattern in the construction process that, from a practical standpoint, seemed fundamentally flawed. Night after night, she observed her team and others welding the enormous steel plates together in a sequence that appeared mechanically irrational. Welders would often start at the edges of a plate and work inward, or begin at one end of a long, continuous seam and proceed in a single, unbroken run to the opposite end. As each of these welds cooled, the molten metal contracted, pulling and distorting the adjacent steel plates. Hamill could literally see the stress building in real time, watching the steel warp and twist under the intense heat of the welding torches. When welders finished one section and moved to an adjacent one, they were effectively permanently locking these immense internal stresses into the very fabric of the ship's structure. To her, it was analogous to improperly tightening the lug nuts on a car wheel. Securing some bolts first would warp the wheel, creating imbalance and potential failure. When she voiced her concerns to her foreman, she was dismissed. She was a welder, not a degreed engineer. The welding sequences had been devised by the engineering department, by men with formal training in naval architecture and structural mechanics. Undeterred, Hamill persisted. In November of 1943, she took the career-risking step of bypassing the standard chain of command to request a direct meeting with yard supervisors. To substantiate her claims, she brought physical evidence. Test plates she had welded on her own time, employing different welding sequences. Some plates, welded using the standard yard method, exhibited significant warping and visible stress patterns. Others, welded using a carefully planned sequence that started from the center of the plate and worked outward in a balanced pattern, remained remarkably flat and true, with minimal distortion. The supervisors were initially skeptical, but one was sufficiently intrigued to personally observe the production line during Hamill's shift. What he witnessed confirmed her empirical observations. The established welding procedures were, in effect, systematically torturing the steel. forcing it to accept and retain destructive stresses that it would carry for its entire operational life. Every cooling weld was creating a zone of residual tensile stress within the metal. The haphazard construction sequence meant these individual stress zones could accumulate and concentrate at specific, vulnerable points in the structure, particularly the sharp corners of hatch openings and other geometric discontinuities. When these pre-stressed ships subsequently encountered the frigid waters of the North Atlantic, the steel underwent a critical transition, becoming brittle. The combination of locked-in residual stress and this newfound material brittleness created the perfect conditions for instantaneous, catastrophic fracture. Hamill's proposed solution was elegantly simple in its principle. Always begin welding from the geometric center of a section and work outward in a symmetrical, balanced pattern. This allowed the contraction stresses to dissipate toward the free edges of the plates, where they could be accommodated without causing concentrated damage. Furthermore, welders should alternate their locations to prevent excessive heat buildup in any single area, and they should avoid completing long welds in continuous runs. These were not abstract metallurgical theories. They were practical, grounded insights from an individual who worked intimately with the material daily, who could feel the metal move and respond under her torch, and who understood the real-world consequences of those movements. By December of 1943, Hamill's findings had ascended through the management hierarchy to reach Henry Kaiser himself. The industrialist now faced a monumental decision. The Liberty Ship program was already under intense congressional scrutiny due to the cracking epidemic. Publicly admitting that the fundamental flaw was not in the quality of the steel or the integrity of the individual welds, but in the very sequence of construction, would be a devastating admission. It would mean acknowledging that every single Liberty ship launched to date had potentially lethal systematic flaws irrevocably baked into its hull. It would necessitate a temporary but significant slowdown in production to retrain tens of thousands of welders. It would require a complete and costly redesign of the entire assembly process. However, it also presented the only viable path to solving a crisis that threatened to cripple America's entire maritime logistics chain in the midst of a global war. To his immense credit, Kaiser did not hesitate. He immediately authorized a full-scale testing program for Hamill's theories, commandeering an entire hull section from the active production line for experimental reconstruction. In a remarkable turn of events, the metallurgists and engineers who had spent months analyzing failed ships were now receiving instruction from a night shift welder who had never attended a university. The test results were both damning of the old methods and revolutionary in their implications. When Kaiser's team of experts compared hull sections constructed using the conventional welding sequences against those built using Hamill's methodical approach, the difference was not merely visible. It was quantitatively dramatic. Sophisticated residual stress gauges demonstrated that sections welded with the traditional method carried internal tensions exceeding 30,000 pounds per square inch, concentrated at critical structural junctions. In stark contrast, the sections welded with Hamill's sequenced approach distributed these stresses over much broader areas, with peak readings barely reaching 12,000 psi. The steel alloy was chemically identical. The welds themselves were microscopically sound. The only variable that had changed was the order in which the welds were applied. Yet this single change improved the structural integrity by a factor that the skeptical engineers initially found difficult to believe. The underlying physics of the failures finally came into sharp focus. Steel is not a static, inert substance. It is a dynamic, crystalline material that responds powerfully to thermal changes. When a welder applies a torch to a seam, they create a localized temperature zone exceeding 2,500 degrees Fahrenheit. The metal in this zone expands dramatically. As the weld pool cools and solidifies, it contracts, but this contraction is resisted by the surrounding, cooler, and rigid steel. This conflict generates immense residual tensile stress. permanently locked into the structure unless the welding sequence is specifically designed to allow for stress redistribution. The Liberty ships were falling victim to a phenomenon known in metallurgy as brittle fracture propagation. The specific grade of carbon steel used in their hulls, while adequate for specifications, underwent a dangerous transformation when exposed to the near-freezing temperatures of the North Atlantic. Below a critical temperature of approximately 40 degrees Fahrenheit, the steel's ductility, its ability to deform slightly and absorb energy without breaking, collapsed. It changed from a tough, forgiving material to a brittle, glass-like substance. In ductile steel, a microscopic crack will often stop, its energy absorbed by the material's ability to yield. In brittle steel that is already under high internal tension, that same microscopic crack becomes a runaway fracture. The massive energy stored in the residual welding stresses acts as fuel, driving the crack forward at incredible speeds, sometimes approaching the speed of sound through the steel. The sharp corners in the Liberty ship's design acted as powerful stress concentrators, magnifying local stresses by a factor of 3 or more. The crack would initiate at one of these points and then accelerate unimpeded through the continuously welded hull plates, encountering no natural barriers to halt its progress. The fate of the SS Schenectady was now perfectly explicable. Built during the early winter, her hull was welded using sequences that maximized residual stress concentration. She carried tens of millions of pounds of locked-in tensile energy within her structure. On that cold Portland morning, with the air temperature at 28 degrees Fahrenheit, her hull steel became dangerously brittle. The intense stress concentration at the corner of a hatch opening initiated a microscopic crack. That crack immediately found a clear, uninterrupted path through the welded deck plates. There were no riveted seams to act as crack arresters, no structural discontinuities to dissipate its energy. The fracture consumed the ship in seconds, releasing years' worth of stored energy in a single, catastrophic failure event. This also illuminated why traditional riveted construction was immune to this specific failure mode. Riveted ships are inherently discontinuous structures. Each plate is a separate entity, joined to its neighbors by mechanical fasteners. A crack that starts in one plate will, upon reaching a riveted seam, stop because the crack cannot easily jump across the physical gap and into the adjacent plate. The overlapping plates and rivets create natural, effective crack arresters. Welded ships, by their very nature, are continuous monocoque structures. A crack in one plate can travel unimpeded through hundreds of feet of seamlessly joined steel. The very efficiency that made welded ships faster and cheaper to build also rendered them uniquely vulnerable to a catastrophic failure mode that riveted ships were naturally designed to resist. The Liberty ship's squared-off, rectangular design, chosen for maximum cargo space and ease of loading, tragically compounded this vulnerability, creating a perfect storm of flawed design, problematic material behavior, and destructive construction practices. Henry Kaiser now understood the full implications of the test results for his industrial empire and for the wider war effort. In January of 1944, he made a decision of staggering audacity. He ordered a complete halt to Liberty ship production at his key Richmond yard and diverted substantial resources to the development and production of an entirely new class of vessel, the Victory ship. This was not a simple modification. It was a fundamental, ground-up redesign that incorporated Bessie Hamill's welding insights and all the other hard-won lessons from the fractured Liberty ships. The gamble was immense. The demand for cargo vessels was still desperate. U-boats had sent over 2,000 Allied merchant ships to the bottom since 1939. The planned invasion of Europe, scheduled for just a few months later, would require the largest amphibious logistics operation in human history. Every single ship was critical. Yet Kaiser was betting that he could successfully implement Hamill's sequenced welding system, redesign the hull to eliminate stress concentrations, improve the steel specifications for better low-temperature performance, and still maintain a production speed that could support the war effort. His competitors were certain he had doomed his enterprise. Congressional investigators watched closely, ready to hold him accountable if production faltered. Kaiser's engineering team worked backward from the identified failure points. Every square corner in the Liberty ship design was systematically replaced with generously rounded transitions. The hatch openings, which had served as the birthplaces for so many fatal cracks, were redesigned with large radii to drastically reduce stress concentration factors. The thicknesses of deck and hull plates were recalculated not merely for strength, but to ensure stress distribution was harmonious with the new welding sequences. Structural frames were repositioned to align with natural stress relief points, working in concert with the welding pattern rather than fighting against it. The steel itself was reformulated. Kaiser's metallurgists specified a new alloy, often referred to as killed steel, where elements like aluminum were added during production to remove oxygen, resulting in a tougher, more homogeneous grain structure. The carbon content was slightly reduced, and the manganese content increased to enhance toughness. Even small, strategically justified additions of nickel, an expensive and rationed element typically reserved for armor plate, were incorporated, as tests proved that even a 0.25% nickel content dramatically improved the steel's resistance to brittle fracture at low temperatures. The Maritime Commission initially balked at the increased cost, but Kaiser successfully argued that preventing the loss of just one fully laden ship would offset the premium paid for the upgraded steel in 50 new vessels. The new specification was approved in March 1944. The subsequent challenge was the monumental task of retraining a massive workforce. The Richmond shipyards employed over 90,000 people by early 1944, thousands of whom were welders trained in accelerated wartime crash courses focused on speed above all else. Now, these welders needed to be re-educated in the principles of sequencing, stress relief, and thermal management. Kaiser established intensive welding schools within the yards, pulling experienced and insightful welders like Bessie Hamill off the production line to serve as instructors. Every welder was issued detailed, numbered sequence cards for each hull section, specifying a precise order of operations, weld number 1 here, number 2 there, with no deviation permitted. The prefabrication system was expanded and refined. Instead of welding large sections together on the open-air building ways, where environmental factors and sequencing were difficult to control, Victory ships were broken down into smaller, more manageable modules constructed in dedicated, climate-controlled fabrication shops. A single bow section might comprise 50 separate prefabricated sub-assemblies. Each of these smaller units was welded under optimal conditions using the prescribed sequences, and then, critically, subjected to stress relief heat treatment in massive industrial ovens before final assembly. This modular approach allowed welders to apply the center-outward principle to each small component without the constraints of working on a vast, complete hull, effectively baking quality and resilience into the ship at the most fundamental level. When the keel for the first Victory ship was laid in February 1944, skeptics were armed with fresh criticism. The construction time for this first vessel was 18 days, slower than the record-setting pace of the Liberty ships. Critics declared this proof that Kaiser's gamble had failed, that quality and speed were fundamentally incompatible in shipbuilding. Kaiser ignored the noise, focusing instead on a different metric, the crack inspection reports. The first 2 Victory ships completed showed 0 stress cracks in their post-construction inspections, not a reduction in cracks, but a complete absence of them. By April 1944, Richmond Yard 2 had been utterly transformed. It no longer resembled a traditional shipyard, but rather a highly sophisticated, precision-oriented assembly plant. The process was a masterwork of logistical choreography. It began in the vast prefabrication sheds, where welders worked on hull sections no larger than 30 feet in any dimension. Each section had its specific, color-coded sequence card, sometimes detailing dozens of individual welds to be executed in a strict spiral or radial pattern from the center outward. Supervisors rigorously enforced the sequence. After a set number of welds, the entire section was moved into a stress relief oven, heated to a specific temperature, and then slowly cooled, a process that allowed the steel's crystalline structure to relax and reorganize, effectively resetting it and dissipating the accumulated internal stresses before they could become dangerous. The steel components themselves now arrived at the yard pre-cut and pre-formed from rolling mills that had retooled for Victory ship production. This eliminated the variability and potential for error inherent in cutting and shaping plates on site. Curved bow sections, deck plates with pre-drilled alignment holes, and pre-welded frame assemblies were all manufactured in factory conditions, ensuring unprecedented consistency. Final assembly on the building ways was a parallel process rather than a linear one. Instead of starting at the keel and building upward, the major modules of the Victory ship, the engine room, multiple cargo hold sections, the bow, and the stern, were all constructed simultaneously in different areas of the yard. Then, in a spectacular ballet of heavy engineering, these massive modules were lifted by enormous gantry cranes and positioned together in a single, coordinated operation. On one notable occasion, 17 major modules, representing 85% of a complete hull, were aligned and set in place in just 11 hours. Welders then connected these pre-stress relieved modules using the same careful sequencing principles, but now they were joining robust, stable components rather than building a stressed hull from scratch. Kaiser implemented a sophisticated, critical path management system, constantly tracking which tasks were bottlenecks and which could be accelerated, shifting workers dynamically to maintain perfect balance across all construction phases. Every delay was analyzed and solutions were implemented in real time during daily management meetings. The relentless optimization paid off. The record was achieved on June 27, 1944. The SS Benjamin Warner, a fully equipped combat-ready Victory ship, was completed from keel laying to the commencement of sea trials in just 5 days and 11 hours. This was not a stripped-down hull. It was a complete vessel with armaments, electrical systems, and a functioning engine room, and its post-construction inspection confirmed stress levels within safe, normal operating parameters. When the Warner sailed on her shakedown cruise, she performed flawlessly in conditions that would have shattered an early Liberty ship. The 5-day Victory ship was not merely a testament to speed. It represented a philosophical victory, a complete rethinking of how complex, critical machines could and should be manufactured when sound engineering principles are perfectly aligned with practical, observed construction reality. The insights of a single welder, Bessie Hamill, had cascaded into a systematic transformation of industrial manufacturing philosophy. The Victory ships that emerged from this revolution were fundamentally different entities from their Liberty predecessors. While they served the same function, the differences began at the molecular level of their improved steel and extended through every detail of their design and construction. The new killed steel specification proved its worth unequivocally. Laboratory tests confirmed that its ductile to brittle transition temperature had been lowered from approximately 40 degrees Celsius in the old steel to near 0 degrees Celsius. This meant Victory ships retained their structural flexibility and toughness in the icy conditions of the North Atlantic and Arctic routes, where Liberty hulls became perilously brittle. The rounded hatch corners, a seemingly minor aesthetic change, reduced local stress concentrations by over 60%, transforming potential crack initiation points into benign structural features. Furthermore, the Victory ship design intentionally incorporated hybrid construction. While primarily welded, strategic riveted seams were placed at intervals to act as deliberate crack arresters. This created intentional discontinuities in the structure, points where a running crack would lose its energy and, in most cases, stop. This was a paradigm shift to defensive engineering, designing not for a perfect crack-free existence, but to robustly survive and contain failures when they inevitably initiated. Quality control became an obsessive, non-negotiable part of the process. Every single completed weld was subjected to magnetic particle inspection to reveal surface flaws, ultrasonic testing to verify internal soundness, and X-ray inspection for the most critical structural joints. The rejection rate for welds was high initially, nearly 15%, but as welders adapted to the new standards and training improved, it plummeted to below 3%, a testament to the effectiveness of the new system. The operational proof was absolute and incontrovertible. Between June 1944 and the end of the war in August 1945, 531 victory ships entered service. Not a single one experienced a catastrophic hull failure. Minor non-critical cracks appeared in a handful of vessels, but these were identified by the rigorous inspection regimes and repaired using the proper stress relief procedures before the ships returned to service. The contrast with the Liberty ships was stark and damning. The human and strategic impact was profound. Crew morale on victory ships was vastly higher. Sailors trusted the hull beneath them. This confidence translated into operational effectiveness. Faster turnarounds, willingness to sail in heavier weather, and greater resilience under combat conditions. The SS Hobart Victory made 17 arduous runs to the Soviet port of Murmansk without a single structural issue, while Liberty ships on the same route were frequently withdrawn due to cracking. The SS Logan Victory survived a mine explosion off Okinawa. The resulting hull crack was arrested at a riveted seam, and the ship was able to make port under her own power. An identical incident would have likely sunk a Liberty ship in minutes. The Pacific Campaign's island-hopping strategy, which required moving immense volumes of supplies across vast ocean distances, was logistically underpinned by the reliability of the Victory ship. The economic calculation, though cold, was clear. A Victory ship cost approximately $600,000 more to build than a Liberty ship. However, with a Liberty ship having a 4.6% statistical probability of catastrophic failure, an event that would destroy the ship, its multi-million-dollar cargo, and claim an average of 18 lives, the additional investment in the Victory ship was recovered many times over through saved lives, preserved cargo, and reduced insurance costs. Bessie Hamill returned to civilian life after the war in 1946 with little public recognition. She received no major medals, gave no testimony before Congress, and her name was absent from the technical papers that later formalized the welding revolution she instigated. The engineering establishment absorbed her practical insights, repackaged them in mathematical language and academic terminology, and published them as if they were discoveries born from laboratory research. For decades, welding textbooks taught stress relief sequencing without mentioning the woman whose empirical observation made it all possible. Yet, her legacy is woven into the very fabric of the modern engineered world. The principles she championed on the graveyard shift in Richmond are now codified in international building codes for everything from skyscrapers and bridges to pipelines and pressure vessels. The American Welding Society's structural code, the Trans-Alaska Pipeline, the seismic retrofitting of the Golden Gate Bridge, and the immensely complex welding procedures for nuclear reactor vessels all descend directly from the procedures developed in response to her work. The catastrophic failures of offshore oil platforms like Alexander Keeland and Piper Alpha served as tragic, later reminders of the principles she had identified decades earlier. The true, enduring miracle of the Victory ship was not the 5-day construction timeline, it was the demonstration of intellectual courage, the willingness to halt a critically important production line, to listen to a frontline worker whose observations contradicted established engineering practice, to admit that theoretical models had missed a fundamental truth, and to redesign an entire system around empirical reality. This philosophy, that the person performing the work often possesses critical insights invisible to the designer in the office, is now a cornerstone of modern manufacturing methodologies like lean production and Six Sigma. Every welded structure that stands today, every pipeline that crosses a frozen landscape, every pressure vessel that contains immense forces, carries within it the silent, unacknowledged legacy of Bessie Hamill, the welder who looked at a breaking ship and refused to accept that that's just how it's done.